All right, folks. I hope you guys had a good weekend. Interesting first week off, to put it mildly. I'm really glad to see that most of you were able to get the videos watched. And towards the end of the week, everyone was able to watch it in the time frame that we were allotted for our period. So keep up the good work and make sure if you have any questions, any concerns, you email me or you comment in Google Classroom and let me know what's going on. Obviously, this week we have a change in schedule. We're going to the Friday #4 schedule for every period. So that means that we have less time for our class. And so I will adjust the lectures appropriately to make sure then that you can finish up the videos and all the work associated with the videos on time. But again, it's going to take a little bit of tweaking, hopefully by the end of the week, if not before. I'll figure it out, and that way then the videos will be long enough for you to get the material and also still give you enough time to finish up the problems that I asked you to do for the lecture, okay? So again, if you have any questions, any concerns, make sure you comment on Google Classroom, email me. The tutorial, the after-school tutorial will still be at the same time, 3:15 to 4:15, or we'll go as long as we have to. So you can check in at that time also through Zoom and ask your questions. And if you have any concerns, you can also express it at that time. Okay. So let's go ahead and get started then. Let's pick up where we left off with yesterday. I'd like you to try this problem here. I'm sorry, Friday. Let's start with this problem here. This will give us a chance to review the use of the molar mass. I'll talk about I'll review what the molar mass is with you, and then we'll use that to do this simple calculation here and carry out this particular conversion. Okay. All right. So let's go ahead then. Let's work on this problem here, and then we'll get back and I'll get started on this for you. Okay. All right. Now that you had a chance to work through this problem, let's go ahead and let's take a look at what you have here. Because so we are doing a mass to moles conversion. So what you have to be able to do there, let me go back here. Remember, this is a conversion, so you have to make sure then that you're able to answer 3 basic questions when it goes about doing this conversion. What do you start with? What do you want to end up with, and what conversion factor will get you from start to finish? And so if you notice here, what we were given then is we were told then that we have 100 grams of each one of these substances here. So we are starting out with mass for each one of these. So we're starting out with the mass for each one of these. And what they want you to solve for then is moles. And so for each one of these here, the conversion then is a mass to moles conversion. And remember, we have a conversion factor that lets us do that. We have what's called the molar mass. Okay? And the molar mass, remember, is expressed then as the mass in grams per unit of moles. For an element, we can get that directly from the periodic table. So for an element, we can get that from the periodic table, okay? Because the molar mass then is just the mass number. So this is the mass number from the periodic table, directly from the periodic table, And so you don't have to calculate for this at all. For compounds, though, we still use the periodic tables, but remember with the compounds, then we add the masses for all elements in the compound. And so for the element itself, if the substance is an element and we're doing this conversion here, and it's referring to an element, then we just take the mass, the molar mass directly from the periodic table. If it's a compound, like all these are compounds, then we have to take the masses of all the elements here, you add them up, and then we use them. We use that for the molar mass. We can use the molar mass. We can use this molar mass here as a conversion factor, because remember, the molar mass, as it's described then, is the mass that's exactly equal to 1 mole of the compound. Okay, so that's how we can go ahead and use in the molar mass as the conversion factor. So I'm going to go ahead and do that for these problems here. So make sure you write that down. Okay. All right. Let's go ahead and start out then. So with the very first conversion, then what we were told then is we have then 100 grams, so 1.00 times 10 to the second grams. The substance here is the compound sucrose. That's form of C12H22O11. Okay, and so that's what we start out with. What we are solving for here then is the moles of that particular compound. Okay, so I'm sorry, let me move this out of the way so we can work out this problem. This out of the way. Here. Okay. All right. Sorry. Okay. And so with that said, then we're trying to find then the moles of the sucrose, which is C12, H22, O11. Okay. And so here we're going to use the molar mass. We have to solve for the molar mass here. So we have then, let's go ahead and I'll do that for you really quickly. So the molar mass of sucrose, C12H22O11. We can solve for that then. Let's go ahead and solve for that. So that's going to be equal to then the carbon atoms. We have 12 carbon atoms from the subscript here. We have 12 carbon atoms. Each carbon atom has a molar mass, and again, we get this from the periodic table, of 12 grams per mole. Since we have 12 carbon atoms, we have to multiply that through that. This here will give us the total mass of carbon in this compound. But though we're not done with that, we have hydrogen then. We have 22 hydrogens. Each hydrogen has a molar mass of 1 gram per mole. And so we have to add to this mass here, the mass of 22 hydrogen atoms. And then finally, then we have 11 oxygen atoms. And so to this total mass here, we're going to add the total mass of 11 oxygen atoms. And each oxygen atom has a molar mass of 16 grams per mole. So we add that all up. We get a mass then, a molar mass then of 342 grams per mole. Now understand what this means then is that whenever you have 1 mole of glucose, C12H22O11, which means, remember what we learned from the very beginning of this chapter, that we have 6.0 times 10 to the 23rd particles of glucose. That's Avogadro's number. Whenever we have that many particles of glucose, its mass then will be 342 grams exactly. 342 grams of glucose. So, okay, so we're going to take advantage of this particular equality here in order to carry out this conversion. So let's go ahead and plug it in. That's our conversion. Now we got to plug it in. And the way we plug it in is, remember, we want to be able to cancel out this starting unit here and end up with this final unit here. So what we will do then is we're going to plug it in with 1 mole of C12H22O11 over 342 grams of C12H22O11. And why do we divide here? Because then the unit of grams of sucrose will cancel out. And that's it. And so when you plug that in, then your final answer is going to be then 0.292 moles of sucrose. 3 significant figures here. You have 3 significant figures here because we have 3 significant figures that we started out with. Okay, so this is the process that you would go through to do this conversion here. The conversion here is what we call a mass to mole conversion. So we start out with mass, we would end up with mole. Okay. All right, so with that said then, let me work out the remaining 2 for you. I want you to, hopefully you were able to find the molar masses of these compounds here. But what you have to recognize then is with each one of these compounds, you have to get the correct formula. In the very first one, I give you the formula. In the second one, I give you the name. And like I pointed out to you time and time again, you have to be able to get the correct formula. Okay, so sodium chloride, the name of sodium chloride, the formula then is going to be NaCl. Hopefully you're able to get that. Okay. Because if you get this formula wrong, obviously when you go to calculate for the molar mass, you're going to get that wrong. And if you get the molar mass wrong, then whatever you plug in here, that will be wrong, even if you plug it in correctly. And so your answer here will be wrong as well. Okay, so let's go ahead and make sure then that you get the formula correct. Okay. All right, so calculating for the molar mass then for sodium chloride, and I'm just going to write it out for you. I won't actually do the calculation. I'm going to ask you to do that on your own. Okay. The molar mass then of sodium chloride, 1 sodium, 1 chlorine, is going to be 59 grams per mole. That's the molar mass. We're going to plug that in here. Okay. All right, so with that said, then it's going to be 1 mole of NaCl over 59 grams of NaCl. Okay, so we'll plug it in so that this unit, grams of sodium chloride, grams of sodium chloride, that unit cancels out. So we plug that in, then we'll get our answer then as being 1.71 moles of sodium chloride. Again, 3 sig figs here because we have 3 sig figs here. Okay, so the key then is making sure then that you get this correct. Okay, and then you set it up correctly here. Okay. All right, let's take a look at the last one. Okay, so we have then potassium permanganate, folks. Okay, so potassium permanganate. Hopefully you got that formula correct, but let's go work that out. We have then 1.00 times 10 to the second grams. Potassium permanganate, folks, is KMnO4. Hopefully you got that right. Okay, so we're going to solve then for the moles of KMnO4. Okay. The molar mass then of potassium permanganate, which is 1 potassium, 1 manganese atom, and 4 oxygen atoms. The molar mass there is going to be 158 grams per mole. Again, if you get this number here, you get this molar mass here, you get that by adding together 1 potassium, 1 manganese, not magnesium, 1 manganese, and 4 oxygens. Right, so you plug that in, we're going to divide them by the molar mass. Why do we divide by the molar mass? Because if we plug it in with 158 grams on the bottom of potassium permanganate, that unit then cancels out. Okay, all right, and so we end up with our answer then of 0.633 moles of potassium permanganate. Okay, and so that's how we go about doing that conversion. I think it's a straightforward conversion. Okay, and so make sure then what you have to do, and I'll just highlight this again one last time for you. You always ask what you start out with. So this is what you start out with. Okay, so you start out, you identify what your starting amount is. So that's what we start out with here. You want to identify what you want to end up with. So what unit do you want to end up with? So that is what we end up with here. And then you want to confine the correct conversion factors in order to get that conversion done. Because today then we're going to go ahead and we're going to do one other type of conversion that will allow you to do conversion, but you basically then ask the same 3 questions again. Okay? So make sure then you work on this, folks, and if you have any questions on this, again, comment in Google Classroom, email me, or make sure then that you stop by this afternoon to get that extra help. Okay? Because we're going to move on, and we're going to talk about how the relationship between moles and volume. So if you have a certain number of moles, if you have a certain number of gaseous molecules or substances, we should be able to find the volume occupied by that particular, the volume then, remember, is the amount of space, excuse me, amount of space occupied by a given object. So you have a certain number of objects, you should expect then that those objects should occupy a certain amount of space. And so the mole volume relationship is based upon finding out how much space is occupied by Avogadro's number of objects. And again, these objects are going to be, we're going to be referring to the representative particles, which are going to be very, very small objects. And so with that said, then the volume of a solid and a liquid doesn't really change that much. They remember, we talked about this back in the first semester. Volumes have definite shape, definite volume. Solids have definite shape, definite volume. Liquids have indefinite shape, but they do have definite volume. That definite volume means then that the volume doesn't change. Regardless of the conditions that the substance is exposed to, the volume doesn't change. However, with gases, we said then that gases have indefinite volume and indefinite shape, meaning then that their volume changes. And that change then makes it a little bit more difficult to deal with gases and to predict then what volume is occupied by a certain number of particles of a gas. Okay? But we can. There is a way that we can do that. Okay? And it depends on, it requires then that we specify the conditions at which these gases exist. So for the calculation that we're going to do in just a moment, we don't have to worry about this calculation. We don't do this calculation for solids and liquids. We have to do this calculation for gases because gases have indefinite volume. Their volume changes. And so in order to get this done then, we have to make sure we understand that the volume of gas changes with certain conditions. For example, temperature and pressure. We'll learn this in chapter 19, but gases change their volume. They occupy more or less space depending upon what temperature and what pressure they exist in. Okay, so we'll get into that discussion much more in chapter 19. What you need to know for this particular chapter then is that we will specify the specific set of conditions of temperature and pressure, what we refer to as at STP, and if at this particular temperature and at this particular pressure, that mole volume relationship that we want to examine will be constant. That doesn't change. And so we can take advantage of that. So let's explore this. Let's explore what happens here. We can do that using what's called Avogadro's hypothesis. Now, Avogadro's hypothesis is something that is a hypothesis that we'll talk about much more in a little bit more in chapter 19. We talk about it much more in AP chemistry. Okay? But with Avogadro's hypothesis, basically what it's postulating is that the volume occupied by a gas, okay, a volume occupied by a gas and the moles of that particular gas are related. And the identity of the gas actually does not matter. The reason for this is that gas particles are very small. The gas particles are very small. And so relative to the space that they occupy, their actual volume itself is not quite important. It's not as relevant. And so what we can do here then is we can say then that a certain number that we can say that there will be a relationship then between the number of particles of the gas and the volume that they occupy. The identity and the mass of that particular gas actually does not matter in this particular relationship. Okay, so let's go ahead and let's explore what we have. Okay, so what I have here for you are three gases: argon on the left, oxygen in the middle, and nitrogen on the far right. Okay, so we have three gases that we are going to deal with here. What we've done then is we've measured out exactly 40 grams of argon, okay, 32 grams of oxygen, and 28 grams of nitrogen. And if you recognize these numbers here, you'll notice that what we've done then is, this is the molar mass. This is that we've actually measured out 1 mole of each one of these gases, 1 mole of each one of these gases. What we've done here is we have specified then that a pressure in each one of these, then we are holding the gases at a 1 atmosphere pressure, and then we're going to make sure we keep the temperature at 273 Kelvin. 273 Kelvin, folks, is 0 degrees Celsius. So the temperature and the pressure for all three of these gases are the same. And if we measure out 1 mole, if we measure out the mass of 1 mole of each one of these substances, we get these masses right here. Okay, so we can measure that out doing careful mass, measuring it out carefully. And what do you notice here, folks? What do you notice? The identity of the gas, okay, so we have 40 grams of argon here, but at this temperature and at this pressure, that 1 mole will occupy this volume. Okay, it will fill up this volume of space. Let's take a look at the oxygen gas. We measure out 32 grams of oxygen. So this is a different mass of oxygen, okay, but we keep it at 1 atmosphere at 273. That 1 mole of oxygen gas will occupy 22.4 liters of volume. So it will fill up a volume of space of 22.4 liters. Okay? And then finally, this 28 grams of nitrogen gas, okay, which is 1 mole, 28 grams of that nitrogen gas at 1 atmosphere and 0 degrees Celsius, also occupies 22.4 liters of space. Okay? And so if you notice here, the identity and the mass of the gas doesn't really matter here. It doesn't matter as long as that gas, as long as we have 1 mole. If we have 1 mole of the gas, that 1 mole of gas will always occupy 22.4 liters if and only if the gas is at 1 atmosphere and 273 Kelvin. And so that's what we refer to then as standard temperature and pressure. So standard temperature and pressure then is a temperature of 0 degrees Celsius and 1 atmosphere. 1 atmosphere is roughly the atmosphere we feel at sea level. Okay, 0 degrees Celsius is the freezing point of water. Okay, and so as long as the gases are at this temperature and at this pressure here, 1 mole of that gas will always occupy this amount of space, 22.4 liters, which means then Avogadro's number, this many particles of the gas will occupy that amount of space, regardless of the identity of the gas. It doesn't actually matter what the gas is. And we saw in the previous slide, it does not matter what that gas is. And so this relationship here is what we refer to as the molar volume. Okay? And if this is an equality, if we're saying that this many moles of a gas is equal to that volume of that gas, okay, again, at STP, we can use that then as a conversion factor. Okay? We can use that as a conversion factor because they're equal. They are equal, and so we can go ahead and carry out the conversions that will allow us to convert between moles and volume of gas or volume of the gas to moles. Okay? So we can do that conversion if we understand then that we're dealing with the gas, and that the gas is at standard temperature and pressure, which is 0 degrees Celsius and 1 atmosphere. And when you do a problem such as this one here, okay, you have to identify that first. Okay, so you want to identify then, let's go ahead and do this, that this problem is asking us about a gas. Oxygen is a gas here, so there it is. So this problem is dealing with the gas, okay? And the gas is at STP, so that's what you want to look for. So gas first, STP second, both of those conditions are here. Then we can go ahead and carry out the conversion. Okay, so with that said then, we ask ourselves the 3 basic questions. So this is a conversion that we can do. The first question is, what are we starting out with? We're starting out with the moles of this gas here, and we're trying to find the volume occupied by that gas. Okay, so the conversion here then, let's go ahead and write this down. Okay, is going to be then this number of moles. So we have this many moles, okay, this many moles of oxygen, and we're going to convert that to volume. And remember the molar volume, we're going to use the molar volume here, but the unit for the molar volume is liters per mole, and so we'll end up with liters of oxygen here. Okay, so that's what we start out with. That's what we're going to solve for. Since this is a gas at STP, we can go ahead and use the molar volume, which tells us then that 1 mole of this gas here, which is oxygen, will fill exactly this volume of space. Okay, so there is the relationship that we're going to use. Okay, then we're going to plug that in as our conversion factor. Okay, again, we want to cancel out this unit, and so therefore we're going to place 22.4 liters on top and 1 mole on the bottom. That allows us to cancel out that unit, and we plug in our numbers here, and we'll get our answer. And I'm going to give you a moment to plug that in. Go ahead and plug that in really quickly. And we'll get our answer then as being 8.40 liters of oxygen. So 0.375 moles of this gas will occupy this amount of space. I mean, which makes sense since this number here is less than 1 mole. We expect then the amount of space that it occupies is going to be less than 22.4 liters. Okay. All right, so we end up with 3 significant figures here. We got 3 sig figs here because we start out with 3 sig figs here. Okay, so make sure then you also are mindful of significant figures as you work through these problems. Okay. All right, so I'd like you to go ahead and take a look at number 22. Okay, try this problem here, okay. And then if nothing else, please try to set up the problem. And then when we get back together, when you enter in your answer and we come back together, I'll work out this problem for you. Okay, so go ahead, take about a couple minutes, try to work out this problem. If nothing else, make sure you set up the problem. Okay. Okay. Hopefully you had a chance to work this out. Let's go ahead and let's identify what we have here. Okay, so starting out then, we have a gas. So first of all, we have a gas right there. Okay, and then secondly, we have STP right there. So we can do this conversion and we can use the molar volume because this is a gas. This problem is asking us about a gas at STP. Okay, now that we have that done, let's answer the 3 questions. What do you start out with? What do you want to solve for? And then what conversion factor will we use? And so if you notice here, they give us this. They're telling us that we start out with 0.6 moles of sulfur dioxide gas. So that's what we are starting out with. That's the number there. And so they're asking us to find the volume in liters, okay, of this particular gas. So let's go ahead and work out this problem. Okay, and let me set it up for you and we'll work it out. Okay, so our starting amount then is 0.60 moles. So the unit we start out with is moles of sulfur dioxide. Now, in these problems here, folks, since this is molar volume, the formula actually doesn't really matter that much. I would like you, because remember, the identity of the gas doesn't really matter, but do practice that though. Okay, so sulfur dioxide is SO2. We're going to solve then for the liters of SO2. Okay. Our conversion factor then is going to be, since this is at STP, the molar volume, which tells us that we have for every 1 mole of sulfur dioxide, that'll occupy 22.4 liters. Okay, so that's the volume of that gas. So let's go ahead and use this conversion factor here. Let's plug it in, okay, and get our answer. We want to cancel out this unit, so we want to make sure that moles of sulfur dioxide, 1, is on the bottom, and the volume then is going to be on top, 22.4 liters sulfur dioxide. That unit cancels out right here. We plug in our numbers and we end up with our answer then as being 13 liters of sulfur dioxide. Again, two significant figures here because we have two significant figures here, okay? All right, so with that said, then I'm running low on time. I'm told then that that's it, okay? So what I would like you to do then is I would like you to do this problem here. So this is the problem that I like to do on your own, okay? And then we'll start with this problem tomorrow. So this will be the one assigned problem that I want you to do. So we'll do this assigned problem here, make you submit your answer, write your answer onto your paper that you're going to turn in, and then we'll start with this problem tomorrow, okay? All right, so good luck with this, folks. The homework tonight is a dimensional analysis worksheet, a little bit more practice for you to do that. Please make sure you get that done and submit it by tomorrow, 11:59. Okay? Get that done. If you need any help, like I said, I'll be available this afternoon, 3:15 to 4:15 on our Zoom classroom, and then come on by and ask your questions. It'll be a live session. Okay? All right, very good, folks. If not, I will see you tomorrow.